Okay, good.
Yes.
Yes, because some of you saying that we cannot hear. Okay. So we're gonna try to finish this part today, which is the first part, because I'm dividing all chapters. I'm dividing all chapters into 2 parts in order to simplify it and to keep a small amount of information that you can save in your mind. Okay, because long chapters would be boring. Okay, so this is part. We have an overview about the magnetic field. The magnetic field, due to the current carrying conductor, magnetic field circuit characteristics, magnetic equivalent circuits, which is the analog between electric and magnetic circuits, and magnetic circuits with air gap. And the last element in this part is the calculation of the inductance of the magnetic circuit. Okay. So, as we said, the magnetic field is some kind of a distribution of magnetic force. So we can produce the magnetic field basically with 2 ways. We can use a magnet, which is the easiest method to produce a magnetic field. We can use directly a magnet, and we can use a coil with a power source. What is the importance of the magnetic field in the electric machines? We said at the beginning that the electric machines, that devices convert the form of the electric energy into mechanical energy, or from mechanical energy to electric energy through a magnetic circuit. So the magnetic field here plays as a medium, يعني وسيط, that ensure the energy form conversion. So from electrical energy to magnetic energy to mechanical energy, or vice versa, from mechanical energy to magnetic energy to electric form. Also, another point which is important, what we call the magnetic materials. So here we said that the use of the magnetic materials help to direct and guide the magnetic field. So the magnetic field can displace in the air, يعني يقدر يديبلاسي in the air or in vacuum or in void. But in order to ensure that we can guide this magnetic field, as I give you example, like water, when we have, for example, water on the ground and we want to guide this water, we use a tube, or use tube or channel or anything like this in order to guide that water. So the same thing of the magnetic field. So why we call them magnetic materials? Because not all materials can guide or can transform the magnetic field similarly. Okay, there are such or specific materials that have the ability to guide the magnetic field, and we call those magnetic materials. So the use of the magnetic materials helps to direct and guide the magnetic field. Why? Because these materials have a high density and which can produce a high flux. And this flux, we are going to see it later, that this flux is very important in the electric machines to produce torque, especially in the rotated machines. Okay. Now let's talk about the magnets. The magnets are materials that can attract the iron or the steel. You know the difference between the iron or steel. Steel هو الفولاذ, يعني iron with some with carbon or something like this. Okay, so the materials that has the ability to attract this iron or steel, we call it magnet, or we can call it a permanent magnet, as you see here in this figure number 1. So the figure number 1 shows these magnets. of course, in the magnetism, we have poles, south and north poles. So this figure shows that always, we said before, as you have seen in your first year, that the electric fields go outward, the positive charge, and goes inward, a negative charge. Firstly, in the magnetism, we don't have charges, okay, and the poles in the magnetism cannot be separated. I guess this is general information. So here, the electric field, the magnetic field, the magnetic fields lines, the magnetic fields come from the North Pole to the South Pole, as you see here in this figure. So the magnetic field lines come from the North Pole into the South Pole. And there is a famous experiment to see those lines using iron, Boumerdes al-Hadid. I think you have seen this experiment before. So everything is clear concerning this slide before moving to the next one. Okay, yeah. Shall we move to the next slide? Okay, good. So to define the electric field, we said the magnetic field, sorry. The magnetic field, as we said, that we can be produced using a magnet or a coil. At the end, this coil is a conductor, okay? Is a conductor, just it's turning in such number of turns. So here, the second element here is the magnetic field due to current carrying conductor. So we are not talking about the magnetic field that's produced using a magnet, but here we are talking about the magnetic field that's produced or that be created using a magnet, using a current carrying conductor. Okay, so always, whatever or whenever we have a conductor carrying a current, DC or AC, carrying a current, we have a magnetic field that will be created around this, as you see here, around this conductor. Maybe it's small amount of the magnetic field, but always when we have a magnetic field, always when we have a conductor like this one, a magnetic field will be created around this conductor. And in order to define or to determine the direction of this magnetic field, we use the right hand rules. For example, imagine, as you see here in this figure, imagine that you are holding this conductor or this stick in your hand, okay, and the thumb is directed. The thumb, your thumb finger is pointing to the direction of the current, as you see here in this figure. Okay, I will show you by myself. Okay, so I'm going to open my camera. راكم تشوفوا فيا؟ Yes, can you?
Yes, we can see you.
Okay.
Yes, sir.
Yes.
Been a long time, I guess. Okay, so for example, this is it's work as a mirror. Okay, so for example, if this the conductor that's carrying the current, this path, for example, when we hold this conductor by my hand like this, okay, my thumb indicates the direction of the current. So the current come from here to from this point to this point, like this, okay? So my thumb pointed to the direction of the current. So the magnetic field is around with my fingers, okay? So always the thumb, in case of a current carrying conductor, we imagine that we are holding this conductor with our hands. The thumb indicate the direction of the current from this point to this point, and those fingers like this, so it's turning, the magnetic field is turning around this conductor. So my fingers, my wrist fingers, are pointed to the direction of the magnetic field. I hope that is clear. Okay. So راني كتبتها هنايا in red. This is a rule. You can take it like this. If the conductor is held in the right hand with the thumb pointing in the direction of the current, the fingers then point to the direction of the magnetic field. So the magnetic field is around. So in order to determine this magnetic field mathematically, okay, so the magnetic field has different terms. Okay, we start by the first term, which is the magnetic field intensity. Okay, so I'm gonna use the board, the whiteboard, as we have done yesterday. So the first element which I have to define is H, which is the field intensity. That's using, so it's the field intensity. Okay, H, using the Ampere's law. Let's go back to the presentation. So using this expression, which indicate that when we have a closed integral of the magnetic field intensity over dl is the element distance. Okay, dl is an element distance, so we integrate over a closed path. Okay, so the Ampere's law is shown in here. The closed integral of the magnetic field intensity H dl equals to I. So the Ampere's law states that the line integral of the magnetic field intensity H around a closed path, of course, okay, sorry, let's take the pointer. Okay, so the Ampere's law states that the line integral of H around the closed path is equal to the current enclosed by this path. Here, just I give you example. It's not necessarily that path would be circular. Okay, just when we integrate this expression, H dl equals to I, so the integral of dl is L, is this path. Here, in this case, we have took a circular path, which is the circumference of this circle, 2 pi r. So let's go back to the board. So we define the magnetic field by Ampere's law, which said that the closed integral of H over a closed path, dl is the element unit of the length, is equal to the current. And this integral equals directly to H multiplied by L, which is the path, the full path, equals to I. Okay, and we call this Ampere's law. So this is the first element must be defined in for the magnetic circuit, which is the magnetic field intensity. Are you seeing the board?
Yes.
Yes. Okay. So the unit.
Yes.
Okay. So the unit of this term, the unit of this term called Ampere meter. Okay, so it's directly A multiplied by M. M is the unit of the length, Ampere is the unit of the current, so the unit of this is Ampere per length, or we are going to see it in case of the coil match. Okay, so let's go back to the presentation. So now let's see the case of the coil. Why we use coil? يعني منين جات الفكرة نتاع الكويل؟ We said that the magnetic field can be created whenever we have a conductor that carrying a current. But so, in order to increase the amount of the magnetic field, we can either increase the current or increase the number of conductors. How we can increase the number of conductors? By turning these conductors. So in this case, we are going to have the current multiplied by the number of turns. So let's go to the board. So in case of coil, this expression become HL is equal to N, which is the number of the turn multiplied by I. Okay, so this is in case when we have a single conductor, and this one is when we have a coil, because a coil is a multiplication of conductors. So HL equals to Ni, and we call this term Ni, we call it MMF, which is Magnetomotive Force, equals to F. We are gonna see it in the next slides. So let's go back to the presentation. Okay, so now in case of coil, we can determine also the direction of the magnetic field. We can determine the direction of the magnetic field using also the right hand rule, but in this case is different a bit. Okay, here imagine yourself that you are holding the coil. Okay, imagine yourself that you are holding the coil and your fingers are the turns of the coil. So I'm gonna open my camera again. Okay, so here imagine yourself you are holding the coil. Okay, and your fingers are the turns of the coil. Of course, the current is flowing through your fingers, which are the turns of the coil. The current are circulating with your fingers. Okay, in this case, if your fingers are pointed to the direction of the current, because the current, it's coil. Your hand is like a coil. Okay, your hand is some kind of coil. The current is flowing through this coil. يعني the current راهو يمشي مع your fingers. Okay, so in this case it's vice versa. Before قلنا when you have a stick, the current passing through this stick. But in this case, the current passing through those turns. So if those fingers determine the direction of the current, your thumb will point to the direction of the magnetic field. So it's vice versa with the previous case. Previously, we said that the thumb indicates the direction of the current because the magnetic field is around. Now the current هو اللي راهو around in this case, because the current راهو يسيركل in the coil. So in this case, the thumb هو اللي determine the direction of the magnetic field. Okay. You know I'm using my phone as a webcam. معيش فوتو شوية. Okay, معليش. Okay, let's pass to the next slide. Okay, let's close my camera. Okay. Okay, now element number 3, magnetic field, magnetic circuit characteristics. Okay. Magnetic circuit characteristics. So the magnetic circuit, as we said, is a combination of a core from iron. We call it iron core. يعني هو can be from iron and can be كما نقولوا alliage. الياج بالعربيه سبيكه which is mixed materials. يعني generally في الالكتريك ماشينز راح تكون mixed materials. يعني basically we have iron, a specific kind of iron of course. Maybe يعني يزيدوا له others 1 or 2% تاع other materials to improve its efficiency or something like this. Okay, so the figure for A or B, we can see two types of the iron cores. يعني هذو راهو simplified shapes because in the electric machines we are not going to find those shapes, so those are too simplified. So figure 4 shows a magnetic circuit with the winding of N turns. Look here, أنا درت لكم right hand rule يعني which indicates to this coil باش نقولوا باللي magnetic field is the current is flowing through this path, so the magnetic field, the direction is up. Okay. Okay, so if the core is composed from ferromagnetic materials. Ferromagnetic materials are the materials are used basically to construct the electric machines. وهما نفسهم materials اللي الماغنت يقدر ياتراكتيهم. يعني basically we know iron also كاين الكوبالت والنيكل. Those three يعني basically maybe there are others or as I said ممكن يكون خليط بين materials, but basically عندنا iron, cobalt and nickel. Those three materials called ferromagnetic materials. There are other types اللي يسموهم diamagnetic والparamagnetic. It's another field. يعني راح ندخلوا بزاف في materials, so no need to to give details concerning this issue. Just you have to know that the materials that are used for the construction of the electric machines called ferromagnetic materials. So the magnetic field produced by the coil. So as we said that of course the magnetic field is produced by the coil, not by the core. The core is used to keep the magnetic field inside this core. قلنا باللي magnetic materials used as a tunnel, as a tube, يعني قناة يمشي فيها يسيركلي فيها magnetic field. Okay, يعني باش ما يضيعش في الهواء, as the case of the water. Okay, so the core is used to keep, يعني شفاو على كلمة keep, or to remain inside, to remain the magnetic field inside the core. Because the magnetic field will be يعني déplacé في الكور faster than déplacé in the air. و in the air راح يديفورم الشيب تاع magnetic field. Okay, so in order to keep it يعني the maximum تاع magnetic field يقدر يديبلاسي, we have to use those iron core. Okay, so the path of the integration here, إلا بغينا نابليكيو Ampere's law, the path here is this. هذا الخط المتقطع اللي راكم تشوفوا فيه, this is the path of the magnetic field. Okay, and this expression is يعني درتها لكم ديجا في البورد, is the case when we have a coil. It's Ampere's law in case of the coil. So it's the same with the previous, we just add the number of turns. So this is concerning the design or the construction of the magnetic circuit. Okay, and so the solution of this integral is directly HL equals to Ni. We have seen this in the board, and we define this term as F. It's magnetomotive force. It's equivalent, يعني when we talk about the electric circuits, we have E. It's EMF, electromotive force. In this case, we have okay. Can you please repeat the last point? Okay, no problem. Your internet were disconnected. Okay, I will repeat this slide quickly. Okay, so we said here that we use the iron core in order to keep the magnetic field that's produced by the core, coil. We keep it in this core in order to guide it to the other side. Or for example, we are going to see other cases like this. So when we want to apply Ampere's law in this case, we take the path of this core. This path, for example, when we have this rectangular core, we do not take, for example, this edge, the length of this edge or the length of the inner edge. We take the main path. Okay, نجو الوسط ونديروا الباث نتاعنا. Okay, as you see here, this الخط المتقطع هذا ولا in this case when we have this circular core. So LC, L يعني length تاع C is core. This is the path اللي راح ننتجريو عليه. Okay, so using Ampere's law expression, the integral in the closed path HDL equals to Ni, the number of turns multiplied by the current. So the result of this integral is directly H, which is the magnetic field intensity, multiplied by L, equals to Ni. So LC is the average length of the core. So let's highlight this. So let's highlight this line. LC is the mean average length of the core. Okay, the quantity Ni is called the magnetomotive force. Okay, it's have maybe the similar work as the EMF. The EMF في electric circuit هي of course it's not always circular. It's not always circular. It's depend. احنا عطينا circular because it's simple work. It's depend on the shape of the core. إلا عندنا rectangular يعني نديروا هو rectangular راح يكون rectangular of course. راح نجمعوا for example this length plus this length plus this length plus this length يعني راح نشوفوهم إن شاء الله في exercises if we able to do recitation. Okay, so this quantity في electric circuit عندنا EMF اللي هي voltage. It's a driving force. هي الفورس علاش يسموها موتيف. هي الفورس اللي تحرك السيركت. هي اللي تكسيتي ولا ديمار this circuit. The voltage يعني generator or source will be created difference in the potential that drive this circuit. في magnetic circuit, this driving force we call it a magnetomotive force F. F equal to Ni, the current multiplied by the number of turns, and equals also to the magnetic field intensity multiplied by the mean length of the core according to this expression. And of course we can determine H in terms of F. H is equal to Ni over Lc and equal to F over Lc. So this is the unit of H. يعني قبيله كنت غلط في البورد. It's Ampere turn over meter. Here in fact turn does not have a unit. We just add this T in order to indicate that we have a coil. So the unit of H is Ampere turns per meters. Okay, let's go back to the board باش نلخصوا واش درنا until now. Okay, so let's اسمحوا لي نمحي هذا معليش نمحي لهنا. Okay, so the first term important in the magnetic field H is the magnetic field intensity. This intensity H using Ampere's law, H times L equals to the number of turns N multiplied by I, and equals to also to the magnetomotive force F. So according to this expression, H is equals to Ni over L. Okay, and it's equal of course to F over L. L is the mean length of the core and F is the magnetomotive force. So the unit of H is Ampere from the current, of course, NI. Turn هذه just to indicate that we have a coil, for example, over meter, the unit of the length. So this is the first term or the first characteristic of the magnetic circuit. Let's go back to the presentation. Now we define the second term. Okay. احنا في ال textbooks when they talk about the magnetic field, كاين اللي يقول لك المagnetic field هو H، احنا نسموها magnetic field intensity، وكاين اللي يقول لك المagnetic field هو B. يعني اللي مشهوره اكثر هي B. احنا كي نقولوا شي هي اليونت تاع المagnetic field يقول لك تسلا هي اليونت نتاع B measured in Tesla. There is a relationship between H and B. To make the difference we call H magnetic field intensity، بالعربية هي شدة. B is the magnetic field density اللي هي الكثافة. And the relationship between H and B is this expression. B equals to mu times H. And we call mu the permeability. As I said yesterday, in your first year, we have studied the electrostatic. We have the term epsilon or epsilon zero, which is called permittivity, سماحية. Here in the magnetic field, we have an equivalent term which is called permeability, نفاذية, mu. Okay, so B is equal to mu times H, and B is measured in Tesla. And mu equals to what? Mu equals to mu zero multiplied by mu r. Mu zero is the permeability of the space, okay, of the space or of the air. We can يعني فراغ ولا الهواء برس كيف. And mu r is the relative permeability of the material. Okay. هنا between brackets عندنا remark. For materials used in the electric machines, mu r value can be high as several thousand. يعني we need في electric machines we need to use materials with high permeability. يعني to ensure that we can create a lot of density. يعني تشوفوا هنا presque proportional. يعني as much we have يعني mu تكون كبيرة, we can create more magnetic field density. Okay, let's go to the board. يعني باش نشفاو على those points. Okay. So the first term حكينا على ال intensity. Now number 2 it's the density. Okay. Number 2 is the density. 2 B. B equals to what? Equals to mu times H. And the unit of B is Tesla. We call B density. Okay. معليش اكتبوا دي ولا density. Don't forget to take notes, please. B is the density. Of course. B is the density. So mu, of course, قلنا mu هي product تاع mu r يعني relative related to the materials times mu zero اللي هي تاع ال free space or تاع the air, which equals to mu zero. هاي دوك تشوفوها في presentation. Let's go back to the presentation. Mu is equal to 4 pi power 10 power to the power minus 7. Okay, so this is the value of mu zero. Okay, so this is the second term or the second characteristic of the magnetic circuit, which is B, the magnetic field density measured in Tesla. Okay, let's go to the next slide. Okay, the third term which need to define is the flux. I know you have seen the flux in the first year in the electrostatic. The flux that's produced by the electric field. Here is a similar case. Okay, So the flux before here just we have we in this يعني هذه اللي راك تشوفيها هنا by substitution of okay بالتعويض تاع expression of H in B يعني can be in term of an I and L يعني it's simple يعني مجرد تعويض. Okay, let's talk about the flux. Similar case كيما وين كنا في electric field. In the magnetic field it's the same. We have a flux whenever عندنا surface. When the magnetic field lines, as you see here in this figure, when the magnetic field lines cross an area, we have a flux. Okay, so the flux is the integral of B, which is the magnetic field, dA. dA is the element area, and the calculation of this integral is directly BA. But just remark, this expression correct when the magnetic field lines are perpendicular to this area. يعني because هذا وش هو؟ هذا scalar product. Scalar product the module of the first vector and the second vector في الcosine تاع الانجل which هي 90 degrees when it's perpendicular, so it's 1. So this correct only when it's perpendicular. So let's consider it perpendicular. So the flux, يعني save it in your mind like this. The flux is related to the area, to the surface. We have flux when we have a surface. So this is the third characteristic of the magnetic circuit. Let's go to the board. معليش هنا ولات عندنا كومبرومو. Okay, so نديرو خط هنايا. Number 3, the flux. Flux equals to phi equals to B multiplied by A. A is the cross section تاع هي area بصح في الماك كي يعود عندنا core A become the cross section تاع الكور. Okay, and the unit of the flux called Weber, WB. Okay, so we have a flux when we have a surface. This is the third characteristic of the magnetic circuit. نعودها quickly يعني باش in order to save those expression in your mind وما تنسوهمش. Okay, I know يعني درنا منهم شوية yesterday, but today we have more attendees. حاجة مليحة of course. يعني firstly we start by the magnetic field H قلنا HL equals to NI, and يعني استلزم أن H equals to NI over L. This is the magnetic field intensity. من magnetic field intensity نروحوا للmagnetic field density. B number 2 هي equals to mu H. Of course mu هي mu 0 times mu R. Number 3 flux from B نروحوا يعني وحدة تجيب وحدة. نروحوا للفلكس. Flux is BA. Okay, so those are the 3 characteristics of the magnetic circuit. Hope that those things are most clear. Yes? Is it clear or not?
Yes.
Those 3 terms.
Yes, it is.
Yes.
Thanks. Thanks God. Okay. يعني كي تشدوا هادو ديجا رانا درنا حاجة. درنا ستيب ديجا. Okay. Now, let's see another term using the previous expressions تاع ال B وال H وال Flux. Okay, let's define another term. Okay, so by the substitution of the expression of H يعني here for example using this equation يعني هنا غلطت ما نمبريتش ال equations but okay معليش. This one, that's 1 and this one is 2. Here we have replaced H with its value Ni over Lc. هذه جبناها من Ampere's law. Okay, and we replace B by its expression in this one. هذه معليش in this one. So the flux equals to mu Ni over Lc times A. Okay, and equals to هما هذه mu A. It's similar, it's the same expression يعني تكون مضروبة عاود هنا دارها over. This term called reluctance هو just باش define this term. Okay, Lc over mu A. So because this one هي similar to this one يعني just mu A جابها تحت كيف. So this term Lc over mu A defined as reluctance. Reluctance okay. Reluctance هي R بس نديروا لها circle كما هكذا. Okay, to make difference between reluctance and resistance. So reluctance here in the magnetic circuits has the same role as resistance in the electric circuit. يعني هي تعيق كما نقولوا الفلو تاع الفيلد تاع الفلكس as the resistance block the flowing of the current in the circuit. Here we have the reluctance. Okay, so finally we get this expression that phi equals to Ni over R, which is the reluctance, and the reluctance is defined by this expression. يعني درنا برك هذه المساواة باش نخرجوا R, which is equal to Lc, the length, over mu A. Okay. Therefore, the relationship between the flux and the MMF can be expressed as, okay, the flux, according to this, equals to Ni over R, and Ni is F. So the flux is equal to F over R. You can see thus is this expression تشبه, it's similar to Ohm's law. Ohm's law عندنا I current equals to V over R ولا E. قلنا باللي Magnetomotive Force عندها same role تاع EMF اللي هي voltage V. R has the same role as the reluctance اللي block the flowing of the current, and the flux has the same role of the current in the magnetic core. Flux هو اللي سيركيلي ولا هو اللي flowy through this core. يعني we have this analogy. يعني when you understand this analogy, the magnetic circuit will be easy. Always, that's why we use the circuit analysis, as you have seen before. For the electric circuit, we use the circuit analysis also in the magnetic circuits. Okay, let's see the next slide and things will be more clear in the next slide. Okay, so the magnetic equivalent circuit. Considering the magnetic circuit shown in the figure number 6, okay, the expression phi equals to F over R has a similar form of the Ohm's law. Our Ohm's law اللي هو I equals to E over R. So the analogy between electric and magnetic circuit is shown in the figure. Okay, you have seen this figure. F, which is the driving force, اللي هي الدماري circuit, F is the driving, Li F is the driving force. Element اللي هو اللي flow through. Okay, no problem. We're gonna stop by. Okay, معليش. No problem. في قلتوا عندكم Champions League مع 8 ياك. No problem. معليش. خلينا نكملوا the next element تاع الاير جاب برك. و the rest would be إن شاء الله next time تاع calculation of. عندنا example خلينا نحلوه الخطرة الجاية ماشي مشكل. نشوفوا برك الاير جاب وخلاص. Okay, let's see this analogy. السيرفس when we talk the surface هو الفلكس كما قلت يجوز في الكور بصح الكروس سكشن تاع ديس كور هي السيرفس كما راكم تشوفوا هنايا في الفيجر نمبر 6 اي هي الكروس سكشن يعني السيرفس اللي يخترقها الفلكس هذا الكروس سكشن. اوكي سو الفلكس هي الام ام اف هي الام ام اف في المagnetic circuit driving force it's the MMF F وفي الالكتريك circuit of course it's the voltage. yes ممكن تخلطت لك برك. اوكي in the table there is a mistake. okay yes sorry there is a mistake وقلت لكم البارح وما كوريجيتوش يعني. اوكي sorry MMF. okay there is a mistake. thank you. Okay, so let's continue. Okay, so here the element اللي راه يسيركيلي in the circuit هو flux similar to the current that flow through this electric circuit, and the reluctance has the same role as a resistance. And the table conclude the comparison or the analogy between the electric and the magnetic circuit. Here the driving force is the voltage EMF. Here the driving force is the MMF F, which is equals to Ni. The current I equals to, of course, Ohm's law, V over R or E over R. Here the flux equals to F over R, reluctance. This is the value of the resistance. Sigma is the relative resistance of the materials. Here the reluctance. Also sigma here is the conductivity and here we define the permeability, and the conductance G is equals to 1 over R اللي هي الناقلية حكينا عليها البارح اللي هي العكس تاع الريزيستانس, and here we call it permeance P, which 1 over reluctance. So here you have a remark that reluctance has the same role as the resistance in the electric circuit. So البارح بسنا هنايا بصح معليش. Okay, let's see the next slide. The air gap. وش هو الاير جاب؟ الاير جاب هو الفيد اللي نلقاوه في المagnetic core, especially في الالكتريك ماشينز. يعني الالكتريك ماشينز باش تقدر تدور لازم يكون كاين ديس اير جاب, ما يكونش ستاتر وروتر مكونيكتين مع بعضهم, لازم كاين اير جاب. يعني I give you this example تاع DC motor. يعني it's not our subject now. ما بغيتكم تشوفوا الاير جاب in case of the DC motor because the void, yes, the void. The air gap. The air gap maybe في الالكتريك ماشينز ما يكونش يونيفورم, يعني الشيب تاع السيركلر وقادر نمشي فيها سلوتس. من بعد نشوفوا ان شاء الله الاير جاب في الالكتريك ماشينز. Okay, in the electric machines the rotor physically is insulated from the stator by the air gap. بصح ما تيماجينيوش بلي الاير جاب في الالكتريك ماشينز راهو كبير. sometimes يلحق بالك 0.01 ملم, يعني الاير جاب صغير خلاص. علاش؟ دوك نشوفوا علاش why the air gap must be يعني as small as possible. l'essentiel those parts ما يكونوش ما يتوشيوش بعضها. Okay, so figure 8 show a cross-sectional view of the DC machines. Okay, so this is the air gap of a DC machine. A magnetic circuit having two or more materials such as the magnetic core and the air gap in figure 9 is known as a composite structure. وش معناها الهضرة هذه؟ Here in the figure 9 you are seeing a magnetic core. When the magnetic core has different يكون متكون من different materials. يعني materials هذو كان قادر يكونوا مثلا الكور مثلا this piece تكون iron and this piece from another material for example. And this piece اللي هي air gap راهي from the air يعني even the air يعني can be considered as another material. Okay. يعني whatever those different materials يعني قادر يكونوا يعني they metal iron or other metal or can be also a core with air. Okay, we call this a composite. The magnetic circuit having two or more materials such as the magnetic core and the air gap is known as the composite. Okay, so كي نحبوا نديروا هنايا الايكويفالنت سيركت نتاع this circuit اللي فيها two different materials اللي هما الايرون هنايا والاير هنايا في الاير جاب. We define the circuit can be in this form. عندنا two different reluctances. Reluctance نتاع الكور is different from the reluctance نتاع الاير جاب. So this is air and also the length. Okay, we're gonna see inshallah in the next slide where LC is the length of the magnetic core and LG, this distance, is the length of the air gap. ثم يعني they are completely separated. Also the reluctance, each one of these materials has his own reluctance. RC is the magnetic core reluctance and RG is the air gap reluctance. يعني كي نجيو نديرو circuit analysis when يعني دوك نعطيكم مثال في الالكتريك سيركت كيعود عندنا ريزيستانسز with different values. كي نجي نديرو كيرشوف's law هكذا نديرو ماش of course راح نقولوا V equals to R1 multiplied by I plus R2 multiplied by I. يعني R1 و R2 they don't have the same resistance. هنايا is the same things the same thing. To those two materials don't have the same reluctance. يعني they are different كيما different voltages. The voltage of the source is the sum of those voltages. Also here F driving force هذه اللي هي MMF equals to F نتاع الكور اللي هي FC plus FG نتاع الاير جاب. Is it clear here؟ لا. Okay. Yes. Okay. Yes. Okay. So يعني هي برك ما كانش حاجة جديدة يعني عندنا صح different terms يعني عرفنا حوايج كيما reluctance density بس البيهيفير تاع those physical systems يعني تقريبا the same. Here we have two different materials, we have different reluctances. يعني it's the same thing when we have a circuit with the different resistances. And also F of the circuit is equals to the FC plus FG تاع air gap, core plus air gap. And we can use also this expression. ممكن في الريسيتيشن عطيتكم core وين يكون الكروس سكشن ماشي the same. يعني each side عندها its own reluctance. Okay. Let's see now the next slide. Okay. Here using Ampere's law, the required MMF can be given as F is equal to Ni and equal to F هي HC of course. HC تاع الكور plus HG LG تاع الاير جاب. So this one is the force MMF تاع الكور and this one is the MMF تاع الاير جاب. Okay, and the total MMF is equal to the summation of those MMFs. So also the MMF can be written in terms of the flux. يعني قلنا باللي الفلكس هو اف اوفر ار اللي هي reluctance also. so F هي الفلكس، يعني نفس الشيء Ohm's law flux phi times R اللي هي reluctance. Okay, so this is the flux is the same because يعني كيما السيري سيركت عندنا current نفسه اللي راهو يسيركيلي في السيركت. Okay, sir, the driving force of the air gap always tend to zero. No, not always. We are gonna say it's not. No, it's not zero. It's not zero. يعني عنده intensity وعنده density. Of course, force F it's not zero. Okay. So هنا نفس الشيء قلنا Ohm's law. F is equal to phi multiplied by R. هنا قلنا الفلكس is the same. علاش flux is the same؟ كيما السيري سيركت وين يكون فيها الكارنت هو the same, the current of the source اللي راهو يسيركيل. But the reluctances are different. Reluctance RG or RC are different. Okay, so using this expression we can F is equal, هنا هزيناه الفلكس as a common factor because it's the same flux plus RC plus RG. Then the flux is F over the summation of those reluctances. قلنا reluctance each one عنده specific reluctance. Here for example reluctance تاع الكور هي LC, the length of the core, over the permeability relative تاع الكور mu C multiplied by mu 0 في الكروس سكشنال تاع الكور. RG هي length of the air gap over the permeability of the air. بس ما عندناش ماتيريال، عندنا only the air. يعني قلنا يا the air or الهواء ولا الفري سبيس almost are the same. mu 0 times AG اللي هي الكروس سكشنال اريا تاع الاير جاب. So AC and AG are the cross sectional areas of the core and the air gap respectively. Also the density BC is the core density. Flux قلنا هو the same flux over AC over the cross sectional تاع الكور, and BG هي ال density تاع air gap equals to phi G over AG. Here هنا in this example اللي عندنا هنايا حتى ال cross section راهي نفسها اسمها density is the same. Here for example عندهم نفس ال cross sectional, so the density also is the same. So the last point to end this meeting, the last point here, this phenomenon which called the flinging of the flux. احنا قلنا باللي المagnetic fields, شوفوا هنايا المagnetic fields lines كي ديبلاسيو in the air يديفورماو. اوكي شوفوا هنايا الفيكتورز هادو كاين فيكتورز راحوا دايركتلي بصح هير at the edge كاين فيكتور. شوفوا كيفاش خرجوا، يعني كشغل كاين فويت، يعني كشغل عندنا فويت نتاع الفيلدز لاينز we call this phenomenon flinging of the flux. So the air gap of the magnetic flux line outwards, يعني we use the term spread out, يعني some lines are spreading out the air gap. يعني كشغل عندك تيوب وعندك فيه وين كاين ترو ولا حاجه كيما هكذا، وين الواتر هذاك يخرج على هذوك لي ترو. نفس الشيء بالنسبه the lines of the magnetic field. So the effect of the flinging increase the cross sectional area. يعني هنا نشوفوا باللي الاريا ما ولاش the same. For example the area تاع الكور راهي from here to here، بصح الاريا نتاع let's change the color نشوفوا وحدك. the area تاع الكور from here to here but the area تاع الاير جاب تولي من لهنا لهنا. Okay, so this is the effect of the flinging. That's why always we try to in the electric machines نحاولوا نديروا الاير جاب as small as much as possible. بصح ما لازمش ستاتر وروتور يتوشيو of course باش تقدر تدور المشين تاعنا بصح we try to reduce it as much as possible to avoid phenomena like this. يعني هنايا راح يكون عندها ثاني other effects. You need more current باش الفلكس ما يضيعلكش etc. So the effect of the flinging is to increase the cross-sectional area. قلنا sectional area ما توليش the same. If the flinging effect is neglected, يعني generally في exercises نقول لكم neglect this phenomenon. We consider the cross-sectional راهي the same. ما كانش البروبلم هذا نتاع لي فويت. Okay. Sir, may I ask? Okay. Why the air gap? علاش نستعملوا وشو الرول تاع الاير جاب؟ دوك نقول لك. احنا عندنا موتور هو magnetic circuit بصح فيه two parts. فيه ستاتور والروتور. ستاتور هو magnetic circuit والروتور هو magnetic circuit. باش يقدر الروتور هذاك يقدر يدور. تخيل كون جا ما كانش اير جاب في الموتور هو ما يدورش ما يقدرش علاش واي الاير جاب يكون باش المagnetic field line يديبلاسيو from the first part اللي هو ستاتور to the rotor ولا العكس. دوك نشوفوها ان شاء الله في الموتورز later. في الدي سي ماشين ما نسموهمش ستاتور وروتور نسموهم فيلد وارماتور. فيلد ويتش اللي يمد المagnetic فيلد اللي يمد الاكسايتيشن والارماتور هو البارت اللي يبرودو ذات برودكت. مثلا في الكيس تاع الجينيريتور الارماتور هو البارت ذات برودكت الاي ام اف الفولتج تاع الجينيريتور. لازم يكونوا separated from each other باش يقدر هذاك يكون free to rotate. that's all. هذا هو الاير جاب. يعني otherwise مثلا في الترانسفورمر ما كانش اير جاب. سوري يا جماعه بحب الباتري تاع البي سي نركب شارجر. اوكي. So otherwise مثلا في الترانسفورمر ما نشوفوش الاير جاب. احنا ماذا بينا الاير جاب we avoid it as much as we can. بصح في الموتورز ولا في الجينيريتورز we can't avoid it. لازم those part لازم الموتور يكون يعني those part are separated to become free يعني باش يكون حر باش يدور. I hope that's يعني المعنى وصل تاع الاير جاب. علاش لازم يكون اير جاب في الالكتريك ماشينز؟ يعني بالدرجه عندنا البارتس الانر بارت هذاك تاع المشين الروتور لازم يكون عنده ذاك الفويد باش يقدر يدور. هذا مكان هذا هو الرول تاع الاير جاب. otherwise مثلا في الترانسفورمر ما نحتاجوهش ما كانش اير جاب في الترانسفورمر. that's it. so ان شاء الله this is the last element. يعني درنا قريب ساعه. غدوه بالك ما نديروش ميتين بالك نخلوها ثيرزداي ولا بعد نقول لكم ان شاء الله. next time we try to solve this example ونكملوا first part نروحوا ان شاء الله the second part تاع this chapter. Okay, if you have any last questions or remarks or something to add, otherwise I'm going to close the meeting. Okay, you're so welcome. ان شاء الله next time ماني نقول لكم وقتاش خليكم تريحوا غدوه. I hope that يعني as I said I'm trying to reduce the damage. Okay, you're so welcome. It's my duty. Okay, see you next time إن شاء الله. I'm going to close this session. Normalement راني درت ريكورد من بعد نشوف الفيديو إذا تريكورده في البي سي نتاعي. Okay, stop share. And meeting.